Welcome to this Maple 2020 conference talk. My name is Johann Mitteramskogler, and I'll be introducing a Maple package for computing rational general solutions of algebraic ODEs. I called this package AGADE, which stands for algebrogeometric methods for finding solutions of algebraic differential equations. Now, let me get through some introduction first. So there has been this new algebrogeometric method for solving algebraic differential equations. And this is a novel method for finding exact symbolic solutions of such differential equations. And in a nutshell, this approach works in the following way. First, you decide on which kind of solutions you want to find. So, for example, you want to find rational solutions. And then you forget for a moment the differential aspect of your differential equations and just parameterize this purely algebraically with, well, say rational functions, since you want to find rational general solutions. And in the second step, you modify these rational functions so that they will also respect the differential aspect of the equation. So this is a two-step approach. First, the purely algebraic, step one, and then a reparameterization step, which will then also satisfy the differential aspect. Now, there are four methods for following this approach for finding rational general solutions listed here. And my Maple package, the aim of my Maple package is to implement these four methods. The first three I've already implemented, and the last one, it's still a bit too experimental to show it in a public video. So we'll not talk about the last one today, but only about the first three. For the sake of this talk, let us fix a field first. K is algebraically closed of characteristic 0. It should be commutable for implementing algorithms, which means we just think of K as the algebraic numbers Q bar. Now, an algebraic ODE, what is that? It's just an ODE of the form A of x, y prime is equal to 0, where x is the independent variable, y is the dependent variable, and A is some polynomial relation. The derivation prime is just the usual derivation, d by dx, with k as field of constants. And recall that we call such an AODE autonomous if the independent variable does not appear explicitly in the equation. Now, this polynomial A will be of further importance in this talk. Thus, we call it the defining polynomial of the AOD. Just very shortly, what is a proper rational parameterization? So we have given a d-dimensional affine algebraic variety, and a proper rational parameterization of this variety is just a function from a full affine d-dimensional subspace onto this variety, which is given by an n-tuple of rational functions in d variables. Now, you will all know probably the well-known proper rational parameterization of the unit circle, which is just given here by these two rational functions, 2t over 1 plus t squared and 1 minus t squared over 1 plus t squared. Rational parameterizations can be computed in Maple, especially the package algcurves can compute proper rational parameterizations of algebraic plane curves, and we will rely heavily on this package algcurves for computing our solutions. All right. Let me briefly introduce these first three solution methods for finding rational general solutions of AODs of order 1. The first method, the so-called method via surface parameterization, starts by take this defining polynomial A of the AOD and consider the surface in three-dimensional space that it defines. So this surface, which I denote here by SA, will be called the associated surface of the ODE. And then following this general algebraic geometric approach, we'll try to find a proper rational parameterization of SA. So this will be a triple of rational functions in two variables. And then in step 2, we want to, well, reparameterize these three rational functions, reparameterize them with suitable rational functions sigma hat and tau hat, such that if we input this sigma hat and tau hat into the parameterization, that the first component will be just x, and the derivation of the second component with respect to x is then the third component. And in this case, phi1 after substitution of t1 and t2 with sigma hat and tau hat is then a rational solution of the ODE. And if we have a suitable parameterization, we'll even get a rational general solution. Now, what is a suitable rational reparameterization? Well, in a nutshell, this is just a rational general solution of the following planar rational system. So this system is constructed from this surface parameterization. And if we can find a rational general solution of this system, call it sigma hat 1 and tau hat 1, then we just perform potentially a shift by a constant to obtain another solution, sigma hat and tau hat, which will then be a suitable reparameterization. So that will get actually a rational general solution y hat if we plug in this reparameterization in the second component of the surface parameterization. Now, there's also a second method for computing rational general solutions of first-order ODEs. This one has been developed a couple of years later in 2018. And this will start by first putting x into the coefficient field. So now we consider A as a polynomial in the larger ring K of x in the variables u and v, and let this define a curve in two-dimensional affine space. So this curve CA, which I've written here, this will be then called the associated curve of the ODE. We again parameterize this rationally, that is to say, find a proper rational parameterization of the associated curve, where psi1 and psi2 are now rational functions in the parameter t, with coefficients that are rational functions in the variable x. Then we again try to find a reparameterization omega hat, such that after we plug it into this parameterization, the derivation of the first component will be equal to the second component. And the condition for when we have such a reparameterization is now the following. If this quasi-linear differential equation, equation 2 here, has a rational general solution, say omega hat, then omega hat will be such a suitable reparameterization. And if we plug it into the first component of our proper rational parameterization, we get the solution of the original AOD. Now, an example how this works from method 2. So this method y curve parameterization. You have the following AOD: x y prime squared minus 1 minus 2 y prime is equal to 0. You find a proper rational parameterization of this associated curve. Well, this is fairly simple in this case. It's just xt squared minus 1 over 2t, and the second component is just t. Now, the associated quasi-linear equation for reparameterization is really simple. It's just omega prime is equal to omega over x. And this has the obvious rational general solution. Omega hat is c times x, where c is this transcendental constant of the general solution. Now, if you plug this into the first component of the curve parameterization, then we'll get the rational general solution of the AOD, c squared x squared minus 1 over 2c. Now the third method is just a special case of the previous two. Actually, this is the first method that started this whole algebra geometric solution approach. And it will be just the same as always. We find a suitable rational parameterization of the autonomous defining polynomial of the ODE now. And the reparameterization is really simple. It's just pattern matching. If the fraction of the second rational function by a partial derivative of the first is either constant or a degree 2 polynomial, then we can reparameterize, and otherwise we cannot. All right, so much for the general methods. Now I will go to the demo file where I show you how we can use the package AGADE to compute these solutions. Okay, this is the demo file that I have prepared. And well, I said I developed the package AGADE. And since it is a package, we can load it with the usual with command in Maple. That's what we're going to do. So with AGADE, and this shows that there is, well, one AGADE constant, which will not be of interest to us today, and a couple of methods of very long names, which find, in most cases, rational general solutions of AODs. All right, let's see how we can use this package to compute some rational general solutions of AODs. The first method, this was this specialized method 3, which I presented at the very end. This can be used to find a rational general solution of an autonomous first order AOD. So for example, we consider this AOD, which is autonomous, and then we can use the package AGADE to compute the solution of this by just, well, putting in this differential equation. Here's the first parameter, then the dependent variable y as the second, and the independent variable x as the third. And let AGADE compute the solution. And as everybody knows that has used the dissolve command, AGADE will, Maple will always return the general, this transcendental constant of the general solution with this underscore Cn notation. So this underscore C1 is the transcendental constant of this rational general solution. Now this is all nice and fine. It gave us a solution. It looks like this, but sometimes we're interested in more, and this more can be computed by providing the extended output equals true parameter. And if we do this, then the output will be a record and it will contain more information. So for example, we can also see what parameterization has been used to compute the solution, and it is of this form. All right, that's good. We can also see what parameterization has been used. We can also use, if we know it by chance, a custom parameterization for computing such a solution. And in this case, I happen to know a very easy one, a simple polynomial parameterization of this AOD. And I can also use this to compute the solution by just, again, plugging it into as an additional parameter. And we'll see, well, it has used now this parameterization, but the rational general solution did not really change. All right. Now, the second equation here, this is one where the package says it does not have a rational general solution, which indeed it does not. But we would also like to know why it has no. So there are a couple of conditions that might fail here. And in this case, it said, well, this parameterization that is computed, it is not suitable for reparameterization. In fact, all these parameterization are equal in the sense that they are equally powerful for finding a solution. And if one is not reparameterizable, then none is. Okay, so much for method 3 of the presentation. There's also an implementation of method 2. This was this parameterization of the curve over a rational function field. And it will work just the same. We have a differential equation. Now it is no longer autonomous, so it contains x in the differential equation. And we just use the command strong rational general solution first order AOD with the dependent and independent variable to compute the solution. And in this case, AGADE will compute the solution x times c1 times c1 squared plus x. Again, well, we can use the parameter extended output to get more information on this solution. And here we'll see that, well, first we have here the parameterization that was used to compute the solution. And we can also take a look at how this associated quasi-linear equation, which is the condition when we can reparameterize, how it looks. And this is really simple in this case. Okay, well, we can also use, if we want to, a custom reparameterization. For example, this is also a solution of this quasi-linear equation, which is different from the one that the package AGADE used. And if we plug this in, then we'll get this slightly different rational general solution of the original AOD. Now, what happens for differential equations which do not have a solution? For example, this differential equation does not have a rational general solution. And AGADE will tell us why. Well, it says the associated quasi-linear equation is neither linear nor a Riccati equation. And this is one of the conditions when we cannot reparameterize. Okay, last but not least, the third approach. This is the one that might require a bit hand tuning. First of all, it requires an external package, rational first integrals, by these gentlemen. It's publicly available. And without going into details, these rational first integrals, they are standard objects to solve these planar rational systems or vector field systems. All right. The command is just as before. Well, now this surface parameterization method, the implementation is called rational general solution first order AOD. You plug in the differential equation, the dependent and independent variable. You also have to give a degree bound on these rational first integrals. This might require a bit of fine-tuning. If you choose it too low, you might not find a solution. But in this case, we found a solution. We used again the option extended output to see how this associated planar rational system looks. And we can also do this, well, for a different equation. Note now that we didn't find a proper rational parameterization of this curve. That's because I use algebraic curves for parameterization, which is not really suited for surface parameterization, but it can find one in some cases. In this case, it did not. So you might just, well, use your own parameterization like this. And then you compute the solution. Well, in this case, it did not compute the solution. In fact, you can prove that this differential equation has no solution. All right, so much for the package. Thank you for your attention. If you have any further questions, please do not hesitate to ask. Thank you.